Okay, so this video is meant to introduce you to the concept of work and understand how it relates to energy. So work is essentially the transfer of energy via a force. So it's, I can't even spell. I'll blame it on messy handwriting. So it's how one object is gaining energy. Another object has to do some work on it. And so far we haven't even cared, like, well, how does the object get velocity? How does the object even get a acceleration? And we knew that, well, a force was being exerted on it, but this is looking at the kind of mechanics of how one object transfers its energy to another object, okay? The symbol that we use in this class is a capital W. And the units that we are going to use are called joules. And a joule is actually made up of kilograms times meters squared per second squared. Okay. I know that in this class we also use the capital W symbol for the weight of an object, and you're just going to have to get used to the fact that in physics there are several times where you have a particular letter that represents different things, and you just have to be savvy enough to understand when we're talking about work versus when we're talking about weight. Okay, so because work is a transfer of energy via a force, you could kind of think of work as being equal to a change in energy, and that is one of the lenses that you can look at work through. And we will look at this idea of work being a change in energy for a particular object when we focus in on types of objects, or types of energies rather, okay? So work can be equal to a change in energy. We can also look at work through the lens of the force that's actually doing the work, not just necessarily like the energy that got changed, but what was causing the change. And so that would kind of be thinking about the work done by a constant force. So when we think about work done by a constant force, we can also have a mathematical model where work is equal to the average force, so that's my average symbol there, times d times cosine of theta. So F, this is the average force. And this is because in real life, the force is usually varying. For our purposes, our force is just going to be a constant value because this is whiteboard land. Things are ideal, but in reality, it's the average force we're looking at. So it's the average force. D is the distance over which the force is being exerted. And theta is the angle between the exerted force and the distance traveled. And that's kind of abstract, so I just want to move right into an example that it kind of explains what this angle looks like, okay? So FD cosine theta, that's kind of our summary of work done by a force. So here's my problem. And here's kind of my generic equation. Work is equal to FD cosine theta. And if this is a constant force, I don't need to think about it, the fact that this is like an average value. So this problem says find the net work done on the 15 kilogram block. So this is my 15 kilogram block. As it is pulled by a 100 Newton force. Oh golly, this kind of got erased, huh? Okay, so as it's being pulled by a 100 Newton force at an angle of 30 degrees while experiencing 20 newtons of friction. So what I'm going to do is I'm going to kind of go through this a little tediously and figure out the work done by all of the individual forces, because it will kind of give you a conceptual understanding of work changing an object energy. And then we will sum up all of those works to figure out what the net work is. So we will just kind of start with tension and kind of go counterclockwise through all of our different forces. So if we did work by tension, So this would be WT, so I'm saying the work done by tension. And this is my equation, FD cosine theta. So this would be my tension force times the distance times the cosine of theta. Now, mathematically, my tension is 100. My distance, did I not even give a distance? I didn't give a distance. What's the distance in this problem? It's pulled 5 meters, pulled, I'm going to add this, pulled 5 meters. Okay, so 100 times my distance of 5 times cosine of 30, because this is moving. This is my distance of 5 meters. So the angle, this theta value between my tension and my distance is 30 degrees, okay? So you would go ahead and plug that into your calculator, and you would get that the work done by the tension is, making sure you're in degree mode, is 433.01 joules, okay? So that's the work done by the tension. So the tension is causing the box to change its energy by 433 joules, okay? Now, let's look at the work done by the normal force. So this would be Wn, so the work done by the normal force, would be equal to the normal force times the distance traveled times cosine of theta. So you'd actually have to go through and calculate out what the normal force is, and you could do that because you know forces. You could do the sum of the forces, but there's a little trick I want you to think about. What's the angle between the normal force and the distance it travels? So let's look at our diagram. Our normal force is going up. So our normal force is going up. My distance traveled is going to the right. So what's the angle between those? It's 90. So this is actually going to become normal, whatever the normal value is, times 5 meters times cosine of 90. But what is the cosine of 90? You are all savvy mathematical students. Cosine of 90 is just 0. So the work, I can't get this marker on, the work done by the normal force is 0 joules. What does that physically mean? It means that the normal force is not contributing to the fact that this block is moving 5 meters forward. That makes sense. Like, the normal force is like supporting it. The normal force is making sure it doesn't go through the floor. The normal force is not helping it at all move forward. It makes sense that it's contributing 0 joules of energy to its forward movement. Okay? Let's do work done by friction. So this would be the work done by friction, would be the friction value times the distance times cosine of theta. I'm told outright in my problem that my friction value is 20. My distance is still 5. Cosine, what's the angle? What's the angle between friction? Friction's going this direction, friction's opposing the motion, and the object is moving this way. So what's the angle between like this distance and friction? That is 180. So this would be a cosine of 180. And again, you're savvy math students. Cosine of 180 is equal to -1. So this means that my work done by friction, 20 times 5 is 100 times -1 is -100 joules. The work done by friction is -100 joules. What does that physically mean? It means that friction is actually taking energy away from the object. And that makes sense. Friction hinders motion. It opposes motion. So the box is moving forward and it's trying to like gain energy from the fact that it's being pulled forward, but friction says, you're not going to gain all that energy. I'm going to oppose you. So friction is actually hindering the movement. So it makes sense that friction is giving a negative work value. Okay, I've kind of run out of room. The work done by the weight. Okay, the work done by the weight. Oh, I think I can do this down here, because it's easy. Work by weight. This is going to be
WW equals WD cosine of theta.
And again, this is very similar to the normal force. My weight is going down. My displacement's going to the right. So the angle between these two is 90. So this is going to be 0 joules. And that makes sense. The weight is not contributing to the movement of the object forward. The object is moving forward. Weight is going vertical. It's not helping it, it's not hindering it, but it's contributing 0 joules. So if I were to think about the net work or the total work done, my tension gave me positive 433 joules, and my work gave me negative 100 joules. So my total work, or my net work, is 433 plus negative 100, so that's going to be roughly 333 joules total were done on my object. Okay. Now, keep in mind, this is an example. This does not mean that the normal force is always going to do 0 joules of work. Okay, I can give you an example right here of the normal force doing work. So right now, my hand is holding the marker. My hand is exerting a normal force. If my hand moves up, the marker is moving upwards. So there's being work done on the marker to move it upwards. Gravity. Gravity can do work as well. Like here it is, boom, okay? Gravity was the force that pulled it downwards. Gravity was the thing that gave it energy. What is true is friction. Friction will always contribute negative work because friction by definition opposes motion. So it will always take energy away from your object. Okay, so I'm going to shift the video now to looking at the graphical analysis of work. And I think that this is done a little bit better with the screencast. But we'll look at what happens in the case where you don't have a constant force being exerted on an object. Like how can you analyze and figure out the work being done by a non-constant force? So the video will shift now.
Okay, so when work is done by a varying force, it's a little trickier to figure out the work done just using the FD cosine theta equation, but we can look at it graphically. So for a force distance graph, the area under the curve is equal to the work done. So this first graph here shows a constant force. And so that's pretty straightforward. We know that just work is equal to FD cosine of theta. And if it's a constant force, then this y value stays the same. And it goes from a particular, 0 to x distance, so that's a d. And that kind of makes sense. The area here is just equal to the force, the constant force, times the distance over which that force was exerted, and this would be a cosine of a 90, okay? So mathematically, we can kind of see in situation 1, where if I have a constant force, the equation works out. Now, in the situation of equation 2, this is an example of like a spring force doing some work, and in that case, you have to almost look at the average force that is being utilized to do the work. But again, if we just look at the area, so work is just the area under the curve. In this case, it is just a triangle, like this area down here. And so we would just say that's just equal to 1/2 my height, which is my force, times my distance. And in this case, the force, if it's a spring force, that spring force is equal to kx, and that's where they get that 1/2 kx squared value. Okay. Now, in the case of where you have like a continually changing force, then you have to actually use calculus. And so in this case, work is still the area under the curve, but in calculus, we know that it would be equal to the integral of, integral of the force function. And we will not go into that depth of mathematical knowledge, but just kind of, you need to understand the basic idea that if you have a force distance graph, that the area under the force curve is equal to the work done.